Welcome back to the next organometallic video. This one is going to be covering the Heck reaction and this catalytic cycle diagram you guys have seen a bunch of times. So hopefully I'll be able to explain it in a way that makes it much easier for you guys to understand what's going on at each step. And that way you won't have to try to waste any time memorizing this diagram. So before we start, I'm going to just make a quick note that it is unnecessary to memorize this diagram. If they're going to ask you questions about the Heck catalytic cycle, what they will do is they will put the diagram on the test, and what they'll do is they'll label certain parts of it, like they can put A right there, and they'll ask you what kind of reaction is that, or they'll label one of the intermediates, and they'll say what's the total electron count or the oxidation state of the metal, something along those lines. So do not waste space on your index card trying to copy this down, or any of the catalytic cycles. You're not expected to have it memorized, all right? It's more important that you're able to understand the what's going on and be able to figure it out rather than memorize. This topic to go down the route of memorizing is not usually going to help you that much. All right. So before we dissect this diagram, let's do a quick overview of what the Heck reaction is from reagents to products. All right. So I have my R group. All right. My R group can be a couple of things, and it's going to be bound to a leaving group. So let's see, for my R group, I can have an aryl group, so something that's aromatic, a vinyl group, so that's something coming off of a carbon of a double bond, and a benzyl group, so a benzene. My X, which is my leaving group, is a halide or a triflate, which I'll abbreviate as OTF, and I'll explain more of what OTF is later down the road. All right, for now, don't worry about it too much. Plus, so those are my, my R group is my carbon chain, X is my leaving group, and now we have to add something else. So what's going to happen here is I'm going to draw a double bonded, an alkene. That's primarily what's used in the Heck reaction, a double bond, or an alkene, I guess. So these are our reagents on the left side. Make some room. And now our arrow. They're usually pretty loose with what you put on the arrow. What I suggest is that you guys look at, let's say, what they've given you on your workshops or on an old exam and just copy that down on your index card just so you have a reference. In case you're ever using it on a synthesis, you don't want to just do something you've seen previously. But the general idea is that you have palladium, and I wrote L2. The L means an L-type ligand, something that doesn't change your oxidation state, because the whole point is that you want your palladium metal to have an oxidation state of 0. It's usually over some sort of phosphine, so I'm going to write PR3, and it could be something like PPH3, right? And NET3. All right, and now what happens is this is my product. All right, and just to make it easier, let's change our group to blue. So our R group binds directly to that carbon of the double bond. So a lot of these organometallic reactions are going to be able to do things that you guys think violate like the rules of what you've seen so far, and so it allows you to do a lot of unique types of synthesis. All right, so one thing to just watch out for, if you see this example right here, right, again, it's another Heck reaction example. In this case, our leaving group is a bromine halide, and it's going to be the R group is a vinyl group, right? This double bonded alkene right here, and our bromine is directly on the carbon of the double bond, right? And here is our, change the color, and this is our alkene, right? What we're going to bind it to. So what's going to happen is, let me redraw the alkene. Essentially, you're going to erase the bromine, right? And you're going to see how I'm just going to overlap this. All right. Notice the way that it overlaps. The double bond that was originally on that alkene, right? When you're forming it to the bond of that R group, this must be trans, right? If I split the double bond in half, you can see that over here I have an H. Let's move this over. I have an H over here. And so the highest priority group on the right side is going to be the carbonyl, which is pointed downward. My highest priority group on the left side is this carbon chain that's coming upwards. And so those arrows are pointing on opposite sides. Therefore, it's trans, all right? And the stereochemistry of the double bond on the R group, like in this case, this guy, he will remain the same. So assume that, let's say I had another methyl coming off of here. So let me actually do it over here instead. Move this back. So this is my bromine. Now let's just erase all this stuff. Put the double bond back. So I have my bromine, right? Let's say I had a methyl coming off of here. Again, I'm just going to erase the bromine. And I'm going to put it back here. Again, this double bond right here should be trans. But this double bond that was on my original R group, it remains the same. So it stays cis in this case. All right? Just keep that in mind. Now, what we're going to do is we're going to go through each step of this catalytic cycle. So at the top over here, we are our reagents and the product, right, summarized. We're going to go through each individual step. So what we're going to do is we're going to start here. This is our step 1. We have palladium, and we have these two phosphors they show you, right? They didn't write the full PPH3s out. But the idea is that your catalyst, this metal catalyst, the palladium has to have an oxidation state of 0, neutral. All right? These two ligands that we have here are L-type. They don't contribute to your oxidation state. Now, let's see what we have here. My first step, this bromine is we're adding this bromine that's bounded to that carbon chain, right, with that alkene. Now let's look. On our new intermediate here, the bromine is directly bound to my palladium, and so is the carbon of that double bond. Now, if you can't remember if these are X-type or L-type ligands, remember we can always break the bond backwards, right, dissociate the bond. We know that the phosphorus is here. These are still those L-type ligands, so they don't contribute to my oxidation state. Let's go with the bromine now. It has 3 lone pairs right now. I'm going to take this bond and I'm going to break it back. Now I have 4 lone pairs, which means Br minus. So that is an X-type ligand. It will contribute at -1 charge to my oxidation state. Let's try it with this double bond. Bring this back, and you're going to get this. Negative charge on that carbon. Again, another -1 charge. That means my total is -2, and therefore the oxidation state of my metal, in this case, is going to be +2. So palladium, let's do that here, it's going to be PD2, right? You can write Roman numerals or +2, same thing. So if I went from palladium 0 to palladium +2, right, my oxidation state increased. So therefore, this reaction is an oxidative addition, right? The addition lets us know we're adding something. So we definitely know it's not something like a reductive elimination. And the oxidative part of the term tells me that my oxidation state increases. All right? Oh, and I don't know why I erased that. Let's just leave that there. So that's the first step of the cycle. Now let's look what's going on here. We have this palladium 2, right? Now let me just change the color of this so it's easier to see because there's a lot of red going on here. All right. So now what's happening is we're adding this new group, right? But let's look at the way we're adding it. We're adding it so that the double bond itself is bound kind of at the center of that double bond, right? Now, one thing to remember is that when we have an alkene, and the alkene is bound to my metal like this, the double bond is bound, the center of the double bond is to the metal, that is a neutral ligand. It's L-type. I am not changing my oxidation state. Again, I still have these phosphorus groups, right? Still no contribution to the oxidation state from them. But my bromine and that alkene over here, there's still a total of -2. And we just said that this alkene, because it's a neutral ligand in the way it's bound, right? You see it's not bound at the carbon like it is here. It's bound at the center. It's neutral as well. And so palladium is still an oxidation state of +2. So if my oxidation state didn't change, but I'm adding a new ligand, or in other words, I'm associating a new ligand, this reaction would have been a Lewis base association, or it could have just been called a ligand association. All right. Now let's move on to the next step. So what's happening here? What we can see is that we had this alkene in red, right, bound to that palladium. But in this case, now we don't have a double bond there anymore. What happens is one of the carbons of this red chain is bound directly to that palladium. And this blue alkene is no longer bound to the metal, it's bound to that red chain. All right, so you can see that the amount of ligands I have bound to my metal decreased. Over here, right, I had 1, 2, 3, 4, 5. Here I have 1, 2, 3, 4. So what happened here? Is my oxidation state different, right? It's always a good idea to probably just check that because it narrows it down a lot in terms of what the reaction could be. So let's see, I have a bromine still, so that's -1. I have the 2 phosphorus groups, they're neutral, so that they're not going to contribute anything. And I have this new looking group over here, so let's just dissociate the bond and see. Take this bond onto the carbon, and so let's draw this out. And we put the lone pair on that carbon, giving it a negative charge. Therefore, that is another ligand that contributes a -1 charge. Right, so I'll just put that here. And so if I have a total of -2, that must mean my palladium in this case is still +2. So we know my oxidation state didn't change. So I can't call this an oxidative addition or a reductive elimination. So what can it be? Well, we said we're decreasing the amount of ligands bound to the metal. So could it be Lewis base dissociation or ligand dissociation? Well, if you see here, in this case, the blue alkene was bound to my palladium. The blue alkene is no longer bound to palladium, but it's still on the compound. It didn't completely leave. That's a requirement for it to be Lewis base dissociation or ligand dissociation. We had to have something completely leave our compound. It didn't. It's bound to a different ligand instead. So we know it can't be Lewis base or ligand dissociation. It can't be anything in terms of oxidative addition or reduction. Therefore, it can't also be anything in terms of Lewis acid association or elimination or dissociation, just because they also change the oxidation state. So the only thing left that we have is ligand insertion or deinsertion. So what we have here, if you look, this blue alkene bound itself to that red carbon chain, right? And another way of saying that, you can see that this red carbon chain kind of put itself between the metal and the blue alkene, right? Look at the path I have to follow. Metal to red, red to blue, right? So I'm going to go metal to red, and then red to blue. Whereas here, I could go from metal to red, and then metal to blue. Metal to blue over here, metal to red. See, what happened is, let me just put it over here next to each other. You can see that in this case, at the bottom, our original reactant, the metal was bound to both the red and the blue chain. Whereas here, the red chain put itself between the metal and the blue chain. That means it's a ligand insertion. The red chain inserted itself between the blue and the metal. So We'll call this ligand insertion. All right. Now let's see what's going on here. In this case, what happened was we had our carbon chain right here. The red carbon is bound, and now what happened is we have this alkene again, right? So what happened here? What's this type of reaction? Well, first thing is let's look at our oxidation state. So we have phosphorus. Again, they don't change their oxidation state, so we don't need to worry about them. I have a hydrogen, right? So that's going to contribute -1. And my bromine contributes -1. This alkene, because it's now bound at the center, right? It is not going to be, it is not contributing now to my oxidation state, right? And so because my overall charge is -1, I now again have palladium +2. So my oxidation state didn't change. So again, can't use any of the reactions like oxidative addition or reductive elimination. All right. So what's this reaction going to be? Well, let's think. We got our alkene again, right? We were able to get her back. We took this hydrogen, you see it in red, and we put it onto our metal. And so essentially, if you can think about it, our hydrogen is a new ligand, right? I took a ligand that was, or an atom, I guess, that was on a previous ligand and shifted it to the metal. This is a little bit of a weird one. It is kind of the opposite of what we did before. It is the opposite of a ligand insertion. This is now a ligand deinsertion. Why? Again, think of the chain itself as being in between the hydrogen and the palladium. To get to that hydrogen, I have to go palladium to red chain to red hydrogen. So metal, red chain, hydrogen. On my product, I have palladium. I could go straight to the red chain, or from the metal to the hydrogen. Metal to the red chain, or metal to hydrogen. This case, my R group, right, that red chain, deinserted itself from between the metal and the hydrogen. It used to be between them. It deinserted itself away. Now, you guys have learned a special type of ligand deinsertion, and this is the one that's used in the Heck reaction. Instead of a plain ligand deinsertion, we call this one a beta-hydride elimination. And so the reason is because the carbon the metal is bound to, that's the alpha carbon. The carbon bound to that alpha carbon is the beta carbon. So we're talking about that hydrogen. All right, and there's a little bit of a stereochemistry at play here. All right, and we'll talk about that a little bit later. So now what happens, I'm at this stage right over there, and we just got to finish this up. So what happens is we have our product that's right here. We just got to get it off of our metal, right? And so in this case, I have this alkene bound to the metal, right? As it stands, this alkene does not contribute to the oxidation state, right? Because it's bound to the center of the alkene. So it's an L-type ligand. So if I make the L-type ligand a ligand that does not contribute to my oxidation state leave, that is just going to be a ligand dissociation, or a Lewis base dissociation in this case. So I'm going to just write Lewis base dissociation. And now let's see, my palladium in this case, back to here, it has a hydrogen -1 and a bromine -1. Total is -2. Therefore, my oxidation state is +2. Right? It makes sense. Let me just write how I've been writing it every time. We know our oxidation states shouldn't change in a Lewis base dissociation. And so that got rid of that. And now we still have one step here. The whole point of these catalysts is we get to regenerate them and reuse them. So we need to get from here to here. And that involves removing the hydrogen and the bromine. If I'm removing two ligands that contribute to my oxidation state, right? They increase my oxidation state when they're on it. So if I take them off, they're going to decrease my oxidation state, or in other words, they reduce my oxidation state. And I'm taking them off. Another way of saying taking them off is I'm eliminating them. So in this case, if you think about it, my palladium is going from +2 to right here, palladium 0. My oxidation state should be reducing. And because I'm eliminating something, the reaction is going to be a reductive elimination. All right? And so that's the entire hex cycle kind of like dissected with all the oxidation states. I didn't do any of the electron counting, but if you guys want, I would suggest trying it just for your own practice. All right? So now let's go on to some other stuff. Still going to stay on the Heck reaction. All right? But we do need to talk about one thing about the Heck reaction, and that's the stereochemistry of it. So to do that, let's talk about this one example. So I have this iodine. It's going to be bound to this carbon chain, and let me redraw that a little bit better. All right, so it's on this carbon bound to a, no, it's, the iodine is on a carbon of a double bond. It's a vinyl group plus my alkene. In this case, it's a cyclohexane, or cyclohexene, I guess. I'm going to go PDL2. And so we're going to do the Heck reaction, right? So we know that what happens, the shortcut essentially is to erase the iodine or the leaving group, and you bind that to the carbon of the double bond, giving that product. The thing is, it's not going to be that simple when we have a cyclohexene. All right, and also just be careful. Organometallics is very easy to lose track of carbon, so please keep track of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so if I erase that iodine, please just make sure you know that's not a carbon. I'm just leaving that bond because I'm going to need to take it with me, put it right there. All right. But like I said, it's just not going to be that simple. The reason it's not going to be that simple is because the Heck reaction follows a very specific set stereochemistry. And you guys probably heard it. It's syn addition and syn elimination. All right. When we do that beta-hydride elimination, it needs to be the same stereochemistry as my leaving group. All right. And so that can affect where my double bond forms. So instead of my product looking like this, like that, it's actually going to look like this. Something more along the lines of this. It looks as if the double bond kind of shifted. All right. So how does that work? We're going to go through it. All right. Now it's going to look a little bit complicated. All right. So we're going to try to go step by step and go really slow. So what I'm going to do is, here's my compound. All right. Iodine with this benzene. PDL2. And so what's going to happen is we're going to join these groups. And I'm just going to put a circle here just because, hopefully you guys know that the rings in a benzene can resonate around. So the shorthand way is just putting a circle. And I'm going to just abbreviate this from now on. That benzene ring is just going to be pH, a phenyl group. All right, just keep that in mind. Because I'm just not going to draw it out because there's going to be a lot of space. So what happens is I'm going to use this intermediate, right? This is an intermediate of the hex cycle. And we have our group that we want to add, right? we had our iodine, which is our leaving group, and our benzyl group. That's what we want to add. What I haven't shown yet is the alkene. So we want to put our alkene. So let's see. I'm going to show two of them. So we have, in this case, one with a wedged hydrogen and dashed deuterium. Now I put deuterium because it acts the same as hydrogen, and I would just want to make a distinction. All right, so let me just move this down a bit. The other one is going to be this. The other alkene, it's going to have a wedged hydrogen again, actually, and dash deuterium. All right, so we're going to actually just use the same alkene. And so we're going to go through the various types of the stereochemistries, all right? So if we go back to our hex cycle, right, we have our alkene. The stage we're at on the hex cycle is we're right here. We need to do our Lewis base association, all right? That's the double bond binds, and we're going to get this intermediate right there. So the double bond on our alkene, let me just, again, we'll make some more room. They can bind essentially one of two ways. That's why I drew two arrows, right, with the same alkene. I can have it bind this way, my palladium metal, and it can bind essentially like a wedge, right? A wedge. So here's my double bond, my wedged hydrogen, and my dashed deuterium. All right? Or it could have bound dashed. Right? Wedged hydrogen, dashed deuterium. Right? And let me just kind of put these all to look like if they're a little bit leveled, because it's going to look pretty messy. And my palladiums, they have their R groups. The phenyl is pH. Those two L-type ligands. And the iodine. Right? And same in this case. Okay? So these are the two ways that alkene can bind. What kind of wedged or kind of dashed. And so we're going to kind of draw like pathways for each one. All right? So what's the next step of the hex cycle is that insertion, right? We got to do our ligand insertion. So we can insert it one of two ways. I can take our metal and I can bind it instead of the alkene, right? Because if you see it, the metal has to now bind to a carbon. So it's going to choose. It's either going to bind to that carbon or it's going to bind to that carbon. And let's actually do it in blue. Or that carbon. All right. Same for this guy. He is going to bind either here or he's going to bind here. So we're going to do two pathways for each. So the arrows I kind of drew is essentially imagine that bond is connected to the metal and it's shifting. And we're going to have to draw one more set of arrows. All right. This double bond essentially is going to attack that phenyl group. All right. And so it's going to go this way. All right. And let's just do that here. It's going to kind of come around, attack there. And same exact thing here. Attacks here. Right. Oh, did I change the color schemes here? Yeah, I did a little bit. And then this one's going to come around and attack. All right. So let's see what happens when we follow the purple pathway, the blue pathway. All right. So we have our cyclohexane. Right. So we have our cyclohexane. We need to show our phenyl. The phenyl was attacked by that double bond. All right. And so my phenyl was attacked by that double bond. How is it going to bind? So first of all, let's actually even look at the palladium. The palladium in the blue arrow kind of bound to this left carbon right here. Change the color. So let's take care of that first. So I'm going to put them on the left carbon, and I'm going to put them on the bottom one, the bottom left one. Now, keep in mind, we call this syn, hold on, syn addition. They must add with the same stereochem. I was wedged here, my palladium was wedged, so it's still going to add wedged. All right, so the palladium is going to look like this. Try to draw it so it makes a little bit of sense. So we have this wedge. Palladium, it's got its ligands. All right, so we have this. Now, like I said, because it's syn addition, the metal and the group that we're thinking about, our group of interest, this phenyl group, the benzene, will have the same stereochem. So it's got to add wedged. And we have this pH. So let's just take a look at our arrows. The palladium, with this wedged bond right over there, binds to this carbon on the left. What that means is now, if it binds to the carbon on the left of the double bond, this double bond attacks the phenyl and it binds to the other carbon of the double bond, right? And so if I try to number them, this was 1 and this was 2, those two carbons, this would have been carbon 1, this would have been carbon 2, okay? Now, we still have our hydrogen, and so let me renumber this. If it's 1, 2, 3, 4, 5, and 6. 3, 4, 5, 6. Carbon 6 had that wedged H and dashed deuterium. So, deuterium. So we did the syn addition. Now we have to do the syn elimination. So we can only eliminate the things that have these same stereochems each other. Now remember, we want to get our metal out, right? Remember, do not eliminate the phenyl, because that's the group that we wanted to add. So what I had to do is take the hydrogen here, because he's dashed, and so was our metal. All right? And so I would take this, and so I'm going to drop this here, and we can kind of kick the metal out. And so my product, and I'm going to skip the steps here on the hex cycle where we have this group associated. I'm going to just skip to the product, and I think you guys will be able to see it. So have our ring. We formed a double bond right there. Our deuterium was here, no stereochem. And my metal here was wedged. Not metal, sorry, my phenyl. So you see how my double bond shifted. And so if I draw out that phenyl for you, and usually we do not show the stereochem in the product at this point, we just draw the line. The stereochem is just to kind of help you guys see the possibilities. So I have this, my phenyl group. So you can see that this is exactly the case we were talking about. The double bond looks like it was shifted. The general hex cycle format, or like the product, looks like my R group was bound directly to the carbon of the double bond. But in cyclohexanes, we have this special case, right? So it kind of shifted. It looks like it shifted. But it's all because of the beta-hydride elimination with the syn elimination. So that's what happened here. Syn elimination. Now let's go to the other one. We did the blue, let's do the red. So we have our 6-member ring, right? So now our metal in this case is going to be binding to carbon 2. So I'm going to put him here, and he was wedged here, and so he'll be wedged again in this case. Palladium, L, L, I. If my palladium binds to carbon 2 of the double bond, the phenyl group has to bind to the other carbon of the double bond, which is carbon 1. And again, it's wedged. pH plus number, carbon 1, 2, 3, 4, 5, 6. Now my hydrogen and deuterium are on carbon 6. But the thing is, remember, we got to kick out our metal. That's essentially our leaving group now. So I don't care about these hydrogens because they're not close to my leaving group. They're closer to the phenyl, which we do not want to kick out. So instead, I'm going to look at carbon 3. It's got a wedged hydrogen, and it's got a dashed hydrogen. No deuteriums. So I'm going to use the wedged hydrogen. Again, remember, syn elimination, same stereochem. So what's going to happen is the wedged hydrogen collapses downward, and the palladium gets kicked out. And again, like I said, I'm going to skip that part in the hex cycle. And now my product looks like this. So we're going to form a double bond here, right? And my phenyl group is now on this carbon. And again, remember, at this point we usually don't show the stereochem for the phenyl. That's just, like I said, to help you guys. And there's my deuteriums and hydrogen. And so again, if I were going to draw the whole thing out, it's going to look like this. Again, so it looks like it's shifted. And so let me just kind of rotate the molecule for you guys. It'll look like this with my hydrogen deuterium over here. All right? And so you can see in this case, the difference between these products is that the deuterium, it had that hydrogen and that carbon eliminated. In this case, it was the other side that was eliminated. Now we still have to focus on the dashed part, all right? So again, let's go blue first. So we have our 6-member ring. And again, let's number our carbons. Let's go 1, 2, 3, 4, 5, 6. So my metal is going to be bound to carbon 1, right? You see that the blue arrow shows it's binding to carbon 1. And so let's put it right here, and it's going to be dashed. Palladium, L, L, I. Carbon 6 is right next to carbon 1. We have the hydrogen wedged into the deuterium. And carbon 2 is our phenyl group. Remember, it's got to bind to the other carbon of the double bond. If carbon 1 is where my metal is, the other carbon is where the phenyl is. All right? Now, got to do our syn elimination, our beta-hydride elimination. In this case, my metal is dashed, so the deuterium, which is dashed, will be the one that's kicked out. This comes down, kicks the palladium out, so we form a double bond. And we're going to form it like this. And actually, before I even do it, let me just number the carbon so it's not confusing. 1, 2, 3, 4, 5, 6. Okay? So double bond forms right there. pH over there. And we have a hydrogen now over there. And remember again, because we usually don't show the stereochem, it's just a bond, a solid bond at this point. We would have this as our answer. Right? And if again, to draw the palladium, the phenyl out, we should do this. Again, all of these look like that double bond is shifted, right? you'd normally just expect this to be the product of the Heck reaction. Directly bound to the carbon of the double bond, but when we have these cyclohexane rings, we got to watch out. It's always a syn addition and syn elimination. All right, and we're almost done. I know it's really tedious. We just got to do the red part. Oh, sorry about that. So in this case, my palladium is binding to carbon 2. All right, so palladium, that's going to be carbon 2. This is 1, 3, 4, 5, 6. Carbon 6, right? That's the one that had my wedged hydrogen and dashed deuterium. Carbon 1, because it was part of the double bond, and carbon 2 has the palladium, we put the phenyl group on carbon 1. All right, so now we can do our elimination. Remember, we want to kick the metal out, so be careful. In this case, deuterium is on the hydrogen and carbon 6 are too far away. So instead of carbon 6, we're going to look at carbon 3. All right, carbon 3. And carbon 3, we have this wedged hydrogen and a dashed hydrogen. Again, remember, syn elimination. So the dashed hydrogen comes down, kicks this palladium out. The product looks like this. Double bond is going to form right here. My pH is right there, my phenyl. And again, usually we do that solid wine at this point. And my hydrogen and deuterium are right there. Now you may be asking, what's the point? And actually, wait, let me just draw the phenyl out. You may be asking, well, what's the point of drawing those hydrogens and deuteriums? Well, it shows you where we're kind of forming the double bond, right? In this case, I was able to use the hydrogen, right? Let me just circle it. The hydrogen right over there on the carbon of the deuterium, whereas over here, I wasn't able to do that based on the placement of that benzene. Same exact scenario here. All right, now in the end, the product is really all the same for these guys. But what I did here, I was hoping to just illustrate to you guys the idea of the stereochem with the Heck reaction, right? Hopefully that makes a little bit of sense. It does require a little bit of practice, right? Now, one more thing before we end this video. There is a way we can avoid this weird shifting almost of the double bond, right? We want to usually try to get something bound to the carbon of the double bond like this. So we can figure out a way to do that. And that's this triflate thing I was talking about, right? So let's look back to this original reaction. I have the cyclohexene, and here's my carbon with my compound with the leaving group, right, and my vinyl group. And we're going to do the Heck. I'm just going to write Heck at this point. We just talked that this reaction is going to give us this product, right? We're going to form we're going to add this group, and where a double bond is going to go here instead, right? It looks like it shifted away, or as if my group bound to some other spot. What we can do is we can find a way to get it so that we get this product, what we intended. All right, so that's how we're going to work our way around it. The way we do this is you want to use something called a triflate, right? So it's a workaround. So what we do is we take a cyclohexane, and you want to have a carbonyl on it. All right, so this is also called like cyclohexanone. It's a ketone. So you need to have a carbonyl on your 6-member ring. What we're going to do is we're going to write TFTO over pyridine. And what it's going to do is it's going to form this weird looking compound. You're going to get OTF, and you're going to have that double bond locked in this position. All right. So we can have it locked in this position. Now what we're going to do is so if you look at the original reaction here, our leaving group was on the compound that wasn't the ring, right? This regular carbon chain. The workaround for this whole idea is you want to put the leaving group on the ring, and it should be a triflate. So now I'm going to react it with a regular alkene, right? So I'm going to react it with just a plain old alkene. And now what's going to happen is my leaving group, this OTF, gets kicked out, and we're going to be able to do it perfectly. So let's number our carbons. Let's get into that habit. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we know that the way that the Heck reaction works, we want to bind the two carbons of the double bond really, or the carbon with the leaving group, to the carbon of my double bond. So 1 is going to bind to 7, all right? So let's try to draw that out. So we're going to have double bond is still there between 1 and 2. Oh. So let's renumber before we even go further. 1, 2, 3, 4, 5, 6. We're going to have 1 bound to 7. And we're going to have this compound. 1 is bound to 7, to 8, to 9. So you see that we are able to get exactly what we intended. If we try to do this reaction, right, with something like this, where my leaving group is on my regular alkene now, and I just have a plain old cyclohexene, or let me just move them along like this, and what you're going to get is this now. You see, my double bond looks like it moved. So the whole workaround is you don't want to have your leaving group on the other chain. You want to have your leaving group on the ring, and the leaving group has to be triflate. All right, so if you can get the triflate, and then you put an alkene, then you're going to be able to get your properly substituted Heck product, right? What you originally wanted. And so that's going to be it for the Heck reaction. I know it's probably a lot to take in, especially the cycle and this whole weird stereochem thing. This is probably more than you guys will need to know, but it definitely is a good understanding of this whole idea of the syn addition, syn elimination. So please have at least some sort of understanding of that, and also make sure you're able to understand these catalytic cycles. It's a really good idea. Get those 10 reactions down. Once you have those down, this is probably going to be the easiest questions on the test. It's going to be 2 minutes. You can be able to do it 5 minutes, and it's going to be 3 points. All right, guys? Questions everyone should be able to answer. All right? So I hope this video helped you guys. Like I said, I know it's a lot to take in, and I'll see you in the next one.